and we assume that there are no factor ordering issues, etc., and this is well defined, or at least we have chosen one particular representation for the Hamiltonian. Then the main evolution equation which you have is minus I dt of any operator is equal to, this is some operator, is equal to H operator. Okay. Now, in this approach, your operators are going to be time dependent and they will change with time, and the state vectors are going to remain the same. This is the standard Heisenberg picture. These are all which we need. So, if you know the system, that is, if you know this H of P comma Q, using this commutator, you will be able to evaluate this commutator for any operator, which is given in terms of Q and P, because you know the fundamental commutator between Q and P. So, this H operating on H and the O, that commutator can be evaluated, which means that you have the time development equation for each of the operators, and you can finally write down the dynamical equation for this operator. For example, if you look at harmonic oscillator, which is the simplest system which we will need, you will find that the equations of motion for Q is exactly the same as the classical equations of motion. You just have to interpret it as a operator equation. Now, if you are working with field theory, there are some extra problems because there is a dependence in space and time. So, I will sort of go through the algebra with some detail in order to show you how these things come out. Except for that, there isn't anything very non-trivial which happens. I mean, whatever you would have intuitively expected will happen for free field. Okay. So, let us ask how we will generalize these to a field. So, in the case of field, what you are going to say is that the degrees of freedom of the field are the values of the field at every point in space. Remember, long back when we did the functional integration, we discretized space and time, and we said that you think of them as discrete points. In this particular case, you don't discretize time, you think of discretizing the space. At a given time t, take every point in space and associate an operator there. So, this I and j, you think of it as x and y. By x, I mean x boldface x. Okay. So, x, y is at every given point is like an I, and this is like a j. And then you want to write down the commutation relation between them at the same time. Here also it is at the same time. So, that goes for a while. So, what you want to postulate is that there is a field phi at time t x, commutator, the canonical momentum, which I will call pi, which is the canonical momentum corresponding to this, at the same time t, at some spatial location y. This commutator is given by I times Dirac delta function of x minus 1. Okay. This simply generalizes this first line here. So, this is what we want to start with. So, the next step you want is a Hamiltonian. You have written down a Hamiltonian here for a point particle system, and we want to write down a Hamiltonian for the field. This somebody has to give you. Okay. And the way we would do this is, if you know the classical system, then there is a Hamiltonian in the classical system in terms of Q and P. You just upgrade the Q and P, which were C numbers, to operators. So, here also we know what a Hamiltonian is in the classical system. So, this is given by half integral over all space. This is the only complication of the Hamiltonian density which we have worked out, and that we know is pi square plus del phi the whole square, which is del phi dot del phi, plus m square phi square. Okay. Just to remind you, this pi is essentially phi dot, right? When we worked out the canonical momentum for the scalar field, pi turned out to be phi dot. So, this is half phi dot square, which is like the kinetic energy. And in the Lagrangian, you would have written down the potential energy by saying it is phi dot square minus del phi the whole square, which would have been di phi. Then you would have put a minus m square phi square with a half factor everywhere. So, this is like kinetic energy minus potential energy in the Lagrangian becoming kinetic energy plus potential energy in the the Hamilton. So this is what we have. So the only non-trivial task is to evaluate these kinds of commutators. Okay, so let us do that. So first we want to know how phi itself changes with time. So let us write minus I phi dot evaluated at, let us say, at some point y. Okay, at some given time t. It is all going to be done at the same time t. So I don't even have to bother to put that time label. But since we are just beginning the game, I will do that. Later on, I will condense this notation. So you want to look at this I phi dot. So this is the commutator between the Hamiltonian and phi. Okay? Yeah.
Why we are assuming O as conservative? As we are not considering total time derivative.
This one?
Yes.
This d by dt?
Yeah,
No, where is the conservative comes in? I don't understand.
Means total time derivative of O we are not considering here. We are
What do you mean by total time derivative?
So in the
Heisenberg equation,
we have total
derivative
dO by dt.
Oh, that is the same as this. That is because we are going to think of O at every point x, and it's just a question of notation. See, if you take this particular object, it is going to be a function of y and function of t.
Yes.
So if I think of phi at a point y to be an operator, its total time derivative is the same as the partial time derivative. But because we are accustomed to, in Lorentz invariant theories, to think of t, x, y, z as independent variables, when you take any derivative with respect to t keeping x, y, z constant, you use a partial derivative. It's a purely a notation. So just as I said, qi is a particular degree of freedom which depends only on time. Suppose you take q. In some surrealistic way, q depends on I as well as on t. Because it depends on whether I is equal to 33 or 2. It also depends on the time. Similarly, the phi of t comma y depends on which y you are choosing as well as on time. Normally, just because q depends on I, when you take the time derivative of that, you don't put partial derivative. But here it is slightly different because this I label gets replaced by this y label. And we are accustomed to thinking of t, x, y, z as three independent variables and writing partial derivative. Purely a notation. This is standard Heisenberg picture. Okay. So you take this and you want to compute the Hamiltonian's commutator with phi. Yeah.
No, I think, did they actually mean that, I mean, you would actually have a term for explicit time dependence of the operator?
No, but that is not being discussed
right,
at all. We are going to look at
the
all the operators. See, all the operators do have a time dependence.
Right, but it's only implicit.
It is coming because of it.
Explicit,
I wouldn't even have to worry whether it's implicit or explicit. I mean, what you are saying is that there is some dA by dt
Right.
kind of a thing. Yeah, that is not required because that kind of a dependence is not there at all.
That would be, I guess, if we have some function of this operator.
No, you don't need to do any of that. You see, let us go back to qi. Qi is just a function of time. Alright. So let me, instead of writing qi, which is a function of time, when I will use the notation dq by dt, dqi by dt. Right? There is no confusion there. Right. Now let me use the notation q is a function of I and t. I can certainly do that because I is 1, 2, 3, 33 and whichever one I am choosing, it depends on t. Now should I write dq, should I write now d by dt of q I comma t, or should I write partial? If I is 1, 2, 3, 4, 33, then I will use total time derivative. But if I happens to be x, y, z, it is just notational convenience since we think of fields and things like that as dependent on x, y, z and t, you use a partial. Okay, so that is all there is to it because here the label goes into this. At least that is the notation which I am using. Okay, so let us compute this commutator. So if I take h and this phi commutator, so I want to calculate the commutator of this. I have kept this as an integration over d3x and phi is at y. Okay. So when you do the commutator, you are calculating the commutator of phi with respect to phi. So I didn't write it down. We also have along with it the relationship that Q commutes with Q. That relationship will translate here into phi at again t comma x, commutator phi at t comma y is 0. They commute. Similarly for pi, etc. Okay? Because this commutes, if I take a gradient of this expression, that also commutes. Because I can take a gradient on x or y, and gradients also commute. This means two of the terms do not contribute. This phi square is going to commute with phi, and the gradient is also going to commute with phi. Therefore, I am only left with having to evaluate half integral over d3x the commutator of h will involve a pi square evaluated at t comma x with phi evaluated at t comma y. Right? Now, this is easy because normally you will have a pi times something and a pi coming on the right hand side, but because this is a C number, it doesn't matter. So I might as well put 2 there. So 2 times pi, it doesn't matter in which order I put, 2 times pi, that 2 goes away with this. Okay, this pi is again at x. Now this quantity is what we have written down here. It is the negative of this. So it is minus I Dirac delta function of x minus y pi at t comma x. So you can do the integral and that will give you minus I pi at y. This is no big deal. One could have guessed it, but it is nice to do the whole thing properly. So it essentially tells you that what we have been calling phi is equal to phi dot. This is just like q dot is equal to the momentum, that equation. Okay. Now we want to do the next one. So the next one would be, let me wipe this out since we know this anyway. The next one would require evaluating the same thing for pi. That should give you the dynamical equation like dp by dt is equal to force kind of an equation. So there I will have minus I dt of phi of t comma y equals, again I need to evaluate the commutator of this with respect to pi. So this term doesn't contribute, but I am going to pick up contributions from the other term. Okay. So let us try to get the signs right. So you have half integral d3x. There are going to be 2 terms. First term is m square commutator of phi square. Just to make sure we understand what is involved, phi square is at x with pi at y. I'll just use a condensed notation like this. This comes from this term. Then I have plus del phi the whole square. So that I will write as d alpha phi again evaluated at x with pi. Okay? Yeah. This one is easy because once again there will be factor 2. So if I take this factor half inside, keep the factor half here, then factor 2 goes away and a phi appears. there is a phi at x, and this is again going to be a Dirac delta function, I times Dirac delta function. So let us write it as I. So there is an I, and the Dirac delta function with this integration will give you just m square times phi. Okay, that part is done. Oh, the integral went away from this. So this is plus integral over d3 x of this. Okay, so let us see what that is. This again, there are two terms, so I can take away the half and keep one of them, because again it is going to become a C number. So I just keep d alpha of this, and then I have only this commutator to evaluate. Yeah, right. D alpha of phi is kept outside. Then I have a d alpha of phi commutator of pi. So what is this quantity? This is a derivative d alpha with this pi. So you go back to this relation, and from this we can write down, if I differentiate this entire expression with respect to x, I can write down d alpha, that is with respect to x, d alpha of phi evaluated at x, commutator pi evaluated at y, which is what we need, is going to be I times d alpha of the Dirac delta function on x minus 1. Okay? So that is what will go in here. So I am going to get I times d alpha of Dirac delta function of x minus 1 times, of course, this quantity is at x. Okay. Now, this we do the usual integration by parts. That is the only way Dirac delta functions can be defined. So that integration by parts will flip the sign of this, and d alpha will go and sit here. So I get a d alpha, which in our notation I believe is minus del square phi. If the sign comes out wrong, we will change the sign. This is evaluated at x, and it is integrated over a Dirac delta function, so all these goes away. At minus and this will give me a plus del square plus del square phi. Del square phi. So let us see whether this makes sense. So in order to do that, what we have to do is to first let us clear out the I factors. So one I goes here, I goes here, and I goes here. Seems to have the wrong sign, but let's see. I think I made a mistake in that sign, but let's see. So this quantity is going to be dt of pi, that will be minus d square by dt square. Yeah, this should be minus. I think I flipped the sign twice. Okay. So you can check that out. So this is this pi, if I substitute back the fact that this is equal to phi dot, this term is going to give you minus d square phi by dt square. Then that del square will come to this side. So the entire equation should read as phi double dot minus, phi double dot minus del square phi plus m square phi is equal to 0. This is just your Klein coordinate, right? Because phi double dot minus del square is your box. It is box plus m square phi is equal to 0. So at some level, this is an elaborate way of getting something which we know. You might have as well written down the action, and from the action you could have written down the field equation, and you could have said that I am going to upgrade the field equation to an operator status. But the reason we did it like this is because this is what Heisenberg picture asks you to do. It tells you that you postulate certain canonical commutation relation between your dynamical variables, which we have done. Then you express the Hamiltonian in terms of those canonical variables, the coordinate and the momentum. And once you have got that, you calculate how the system evolved using this equation. That will give you two equations which can be combined together to get the field equations for that. Okay. So now what do we know? Yeah, you have.
So in the computer, when you took the derivative,
Yeah.
how come you don't have any terms with derivatives on the pi's?
Derivatives on
You took the derivative of the entire computer, right?
It was with
No. I am differentiating with respect to x. You see, d alpha,
Okay.
alpha only spatial index, and I am differentiating with respect to x. Okay, that's a standard trick which you use whenever you have two variables. Yeah. Okay, so you end up getting this field equations in the end. Now, what does that buy you? What it is telling you is that if you think of this entire thing as a quantum mechanical system in Heisenberg picture, then the operator which you have introduced, I mean this operator now we know is just phi dot, so we don't have to think of it as an independent operator. The operator phi which you have introduced evolves like this, okay, and there is a commutation rule which it satisfies, which are related by this. What we need to do next is to construct the Hilbert space. So suppose again go back to harmonic oscillator. If you have gone in the case of a harmonic oscillator, the two equations which we have written down, one would have been P is equal to Q dot, the other would have been P dot is equal to some minus omega square Q. You will substitute for P as Q dot and you will get Q double dot is equal to minus omega square Q. That is fine. So you have got an equation for Q, but you next want to solve that equation and introduce some set of new variables which automatically will take into account all these commutation rules so that you can construct the Hilbert space. Okay? That is the next step which we want to do here. So here what we would have done is that we would have taken this equation and we would have solved it. But that is trivial, because what I can say is that you take this phi and you assume phi is some operator times a C number function. Then the C number function just satisfies this wave equation. The solutions to this wave equation we know is e to the I k dot x, e to the plus or minus I k dot x. Therefore, we can immediately write down the solution to this, and we have done it several times in the past. So phi at x will be equal to some integral over d omega p. Remember this notation, which has a 1 over 2 omega p in it. It's a Lorentz invariant expansion. Then I have a of p e to the minus ipx in our notation plus ap dagger e to the ip. Okay. Now what we want to do is to say that given this relation you can also compute what is pi. I can just take a time derivative of this, I will get you pi. Then you impose these commutation rules and ask what is the commutation rules that are satisfied by AP and AP dagger. Okay, we have done this before, so I will now do it in the reverse direction. Given this, I will ask what is the, suppose I postulate the standard commutation rules for the creation and annihilation operator here. We will check for consistency that these are satisfied. Okay, that is as good. So the only non-trivial thing is that phi pi kind of a thing, and which we will do. But in particular, now we can do something much more powerful. These commutation relations are what is known as ETCR, equal time commutation rule, and this relation just gives you the commutator at t is equal to constant. That is, these two labels are the same. Don't make the mistake of assuming that this is true with a 4-dimensional Dirac delta function on the right hand side when it becomes arbitrary times, that is phi at x and phi at y. That, for one thing, it is not dimensionally correct. Dirac delta function has the dimension. Left hand side remains the same dimension whether you take it equal times or unequal times. Right hand side dimension will change. But anyway, it is not true. So what we can compute given this expansion is that, yeah.
It is not true because Lorentz invariance.
No, 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 no. It is not true because it is simply not true. We will work it out and we will find it is not true. But one easy way of saying this is that if this is true, the same relation cannot be true with 4-dimensional Dirac delta function because 4-dimensional Dirac delta function has a different dimension, 1 by L to the power 4 compared to 1 by L cube. Reference side dimensions do not change. So both these relations cannot be true. Okay. So given this, let us compute that explicitly. For that it is convenient to go back to our old notation which we use. We will think of it as a field A of x plus a field A dagger of x, where A of x defines this quantity. It is completely Lorentz invariant, and this commutation relationship between APs are also in a Lorentz invariant form. That is AP commutator AQ dagger. We take it to be okay. The way we had worked it out, we had a 2 pi the whole cube 2 omega p Dirac delta function of p minus q. Okay, this extra factor is what takes care of the fact that I am not using an 1 over square root of 2 omega times AK dagger, which would have been the standard commutation rule. This extra thing takes care of Lorentz invariance because the right hand side is a Lorentz invariant commutator. So we have this A and A dagger, and we want to compute the commutation phi at x, commutator phi at y. Now it's all 4-dimensional. Okay. So this is commutators of these quantities. So you end up getting first commutator of A with A at x, A at y. Now A at x, y, whatever you do is only going to involve commutators of AP with respect to AP. They are 0. So you don't have to worry about that. Similarly, A dagger x and A dagger y also will only involve A daggers. So for that is also 0. Only the cross terms are going to survive. So what I have got is in this side is A at x, A dagger at y plus A dagger at x, A at y. Again, watch out for sign errors. Okay, so this is what we have. So let us compute any one of them. First of all, it is obvious that this is just obtained by flipping the x and y. So suppose I put a minus sign here. Then this is A of y, A dagger of x. So this is exactly the same as this with the x replaced by y. So I only have to compute this quantity. So let us go and compute that. So A at x, commutator A dagger at y. This you just look at this. So it is going to be d omega p, d omega q. There will be two products in each one of them. Then there will be an e to the minus ipx. Then you will have plus iqy coming from the second with a dagger flipping the sign of this. Then you have a commutator of AP, AQ dagger. Okay? And AP, AQ dagger is what we have written down here. So let me replace that. So I get 2 pi the whole cube, 2 omega q, let us say, doesn't matter if it is q or p, p minus q. Now I am going to do the integral over this d omega q. So I know that this is actually d3 of q upon 2 pi the whole cube into 1 upon 2 omega q. So the 2 pi the whole cube and 2 omega q just goes away. and I have a D3Q integral with a Dirac delta function. So that just makes P is equal to Q. Okay. Remember that these are done on mass shell. So when I make vector P equal to vector Q, omega P also becomes omega Q. So the whole thing can be written as 4-dimensional. So that's it. First of all, this commutator is completely Lorentz invariant. This part is Lorentz invariant, this is Lorentz invariant, and it is just a non-mass shell integration of this quantity. So now if you go back to the previous expression, this is this quantity minus the same quantity with x and y replaced, which is IP x minus 1. This is the commutator. Okay. So as you can see, it is non-zero. In general, non-zero, and if you work things out, it will be in terms of Hankel functions, etc. However, we have done this before, but just to remind you, suppose you consider equal time, then it better vanish, right? So if you take equal time, you will have only P dot the vector here, and then here you will have again P dot this. They differ only by the sign of this. That is, P flipped to minus P is all that goes on. But I know that this is invariant under P going to minus P. So when the time labels are the same, these two things just cancel out. Because it is Lorentz invariance, we also immediately get the result that on any space-like hypersurface, this vanishes. I spent quite a bit of time explaining why this is very crucial and vital. That is, the commutator between the two dynamical variables. And now it is much nicer, because at that time we introduced it as some kind of an ad hoc construct coming from the propagator. Now this is our dynamical variable of which observables are constructed. Like if you look at the energy or the, take anything like Hamiltonian. Hamiltonian is a quadratic expression in phi. And in general, whatever quantities you construct will be quadratic expressions in phi and pi. So it is extremely important that these quadratic expressions, if I have an observable operator, the quantity, the commutator between those observables on space-like surfaces has to vanish. Okay? So this is one crucial basis in quantum field theory. So it is important to understand that. I have only shown it for the fundamental field, and I think I threw it in as an assignment that if this is true, then it is true for any quadratic expression, which is fairly straightforward to prove. Why do we need that? Because if that is not the case, causality will go for a toss. When x and y are related by a space-like interval, the time ordering has no definite meaning. You can have x naught greater than y naught in one Lorentz prime, and in another Lorentz prime, x naught will be less than y naught. So if you do something at x, and if the commutator is not 0, then in general that measurement will affect the observable at y. If you do something, if an observable gets affected, that is not a big deal, but that should happen only within the light cone. If I do something and an observable at a space-like location gets affected, then in one frame I can say it got affected after I did something, but in another frame it would have got affected before I did something, which is contradicts causality. Okay? So these are very tightly constrained in Lorentz invariant theory. You have a little freedom on that. Okay, so we have got this commutator. Now, the important commutator we wanted to evaluate is this. And it is nice to see how that comes about. So now let us compute phi at x, phi at y. And we will eventually assume it is at equal times. Okay? So we already know this commutator, and we can play the same trick which we did before. We just you only have to differentiate this with respect to y naught. Okay? So if I differentiate that with respect to y naught, I will get integral d omega p. Let us see what I will pick up. I am differentiating with respect to y naught term. So this has a e to the plus I p y naught. And in my signature that comes with positive. So this will bring down an I p T0, which is just omega p. Of course, if I miss a sign, we will flip it again. So I omega p here times this quantity, but this quantity is now evaluated at equal time. After differentiating, you put equal time. So this is going to be x dot y. I flip the sign because I am looking at the spatial quantities, again signature. Then when you do this, it has to come with just the opposite sign. Therefore, you will get plus I omega p e to the minus I p dot x minus y. So you take out this I omega p, keep the I outside, and then I have omega p, and expand this out. This is going to be d3p over 2 pi the whole cube, 1 upon 2 omega p, that omega p cancels it. Now that is very nice because the differentiation brought down on omega, which cancelled with that 1 over omega. The integrals over either of these is Dirac delta functions on x minus y. There is a half waiting to take care of that. So you end up getting just I times delta of x minus y. Okay. So this tells you that if I had expanded your phi like this, I have solved all my problems. First of all, an expansion like this ensures that my operator equations of motion are satisfied. That is taken care of. Then I can identify my A and A dagger as creation and annihilation operators. So I have a complete Hilbert space. Since A and A dagger satisfies this commutator, I know everything because it is just harmonic oscillator. So I can start with a state in which there are no particles. Then I can build states for every value of p by acting on them, and that will lead to a generic state which is labeled by a set of integers, which is what we did before. Okay, so everything is fine, and we have completed the first quantization of a field. If you started with a real scalar field, and you have completed. Okay. Now I want to do a little bit more. What would have we done in the case of harmonic oscillator at this stage would be to say that, look, I want to look at the eigenstates of the Hamiltonian. For that, I want to express the Hamiltonian in terms of these A's and A daggers, and we would have got an expression. So I want to again work that out. That is going to be another series of algebraic computation. We know what answer to get, but as long as you watch out for the algebra, it should come out all right. So let us try to work that out. I do need this expression, but probably nothing else. Okay. So the idea now is to go and compute this Hamiltonian, and for convenience we will think of the first term as phi dot square and in terms of these variables and express it in terms of A and A dagger. Okay. What happens in the case of harmonic oscillator? You will get for a harmonic oscillator something like H. Is H cross omega into A dagger A plus half. So in this case, you would have expected to see some k, some k, some k, summed over all k, which will become an integral d3k over 2 pi the whole cube, and it will come in terms of these A daggers, which are related to those A daggers by a square root of 2 omega. That is, these A daggers obey the commutation rules AK, AP dagger is just 2 pi the whole cube Dirac delta function of k minus p. While the capital A and A dagger had an extra 2 omega p there, this means that your capital AK is actually small ak into root 2 omega. Because if I have taken the capital A's commutation rules and substituted this, I would have got two omegas on the left and right, which I can cancel out, thereby getting this. Okay? So this is what we want to obtain, and let us see what we get by when we use this. So let us start with the simplest term in that. So we will start with half m square integral over d3x of phi square. Okay? So we are supposed to take this phi and square it and compute it. Now we know that this Hamiltonian is conserved in time. Therefore, its expression for this is going to be the same at all times. So we can simplify computations by taking t is equal to 0. Okay? It is also convenient at this stage to flip the p sign in the other one, in the second term, and write this as integral over d omega p. We have taken t is equal to 0. So these are spatial coordinates. This is also spatial coordinates. And I have flipped the sign of p in order to get both the signs the same. So I end up getting, let us say, AP plus AP dagger times, let us assume I flip the sign here and retain the sign of this as it is. So I would have got then e to the I p dot x, the plus sign.
So why have we taken t is equal to 0?
Okay, because this is independent of time, so I can do it at any time. T is equal to 0 simplifies the calculation because e to the minus I omega, that phase goes away. It's purely for convenience. So now I want to evaluate this using this expansion. Okay, so I will need two integrals. There is an integral over d omega p, then there is an integral over d omega q.
Won't there be minus p with the a dagger?
No, that is the whole point.
Okay.
Take this. This will have a e to the plus I p dot x.
Yes.
This will have a e to the minus I p dot x.
Yes.
Then I am flipping the sign of p in the other one. Oh, you are saying here.
Yeah.
Absolutely correct. I forgot to put that. Yeah, it is a minus p dagger. Correct. So you have this, and you want to integrate the square of this quantity. So we'll have two copies of this. So it is of course convenient to write it as phi and a phi dagger, because phi dagger is same as phi, but the dagger will give you the correct complex conjugation. So you will have e to the I p dot x minus I q dot x because of the dagger. Then let me write this as AP plus A minus P dagger into AQ plus A minus Q dagger. Okay, I just at least want to evaluate what quantity for you to see how it goes. So this is the structure of that m square phi square term in the Hamiltonian. Now we do the integral over d3x. So if you do the integral over d3x, this is going to give you a Dirac-Delta function 2 pi the whole cube into Dirac-Delta function of p minus q. So let us do the integral over d omega q using that. So 2 pi goes away, but an 1 over q omega p or q, let us keep p, will survive, and the p integration q integration just replaces all the q's by p's. Okay, this is the structure of the term. So let us write it down slightly neatly. D omega p 1 upon 2 omega p. It's convenient to take this m square here and put it here. Then the remaining terms, which are AP plus A minus P dagger. Same thing once again. I made a mistake. This is dagger and this. You see, remember, in order to get the phi square, I multiplied phi by phi dagger. That is how I changed the sign of this to minus. So when I take the dagger, this should also have gone into dagger. So it is AP dagger, A minus B. Okay, just make sure you understand that. The phi square was interpreted as phi dagger. So phi, you will get this term. And in phi dagger, you will get the term with a dagger on this, I mean with a Q. And when you get this, the first term will be dagger and the second term will be without dagger. Okay? Yeah, so you guys should appoint it. So this is the first term. Now we want to go and do the second term, which is the del phi the whole square term. What will that give? Okay, so let us look at this. Del phi only involves derivatives with respect to this. So if I had calculated d alpha of the phi, I would have brought down an I p alpha, right? Then I do one square of that with a dagger operator. So the I p alpha will have a minus I p alpha with the upper bracket, right? So the minus I and an I will take care of it themselves. It will give you a 1. You will end up getting a p square. Except for everything else, this is exactly the structure you will have. Therefore, that will just add to m square, and m square plus p square, which happens to be omega p square. Okay? So let us take that out. So the first two terms together, not first two terms, the last two terms together have got you up to this point. Now we want to add to this the term coming from pi square. Pi square involves phi dot. So this trick you have to be a little bit careful. So you are going to take a phi dot of the term. So you have to go back here. You can't put t is equal to 0 and then try to take a phi dot. So you take this and take the derivative of that with respect to t. So when you take the derivative of this, you will pick up here a term with a minus I omega, because this has a t and then there is an omega. So the time derivative of this will give me a minus I omega. This will give me plus I omega. So the relative sign will flip. Right? And yeah. Okay, so take the time derivative of this. So let me write it down. Compute phi dot. That will be d omega p ap. I am taking the time derivative of this. So px has a p0, which is omega p t minus p dot x. Right? So I am taking derivative with respect to t, so I will get a minus I omega p. So I get minus I omega p. Of course, after taking the derivative, I am setting t is equal to 0. So, and everything, all these ideas will work. In the other one, I will get plus I omega p. So I will have plus af minus p dagger I omega p times e to the I p dot x. This is again evaluated at t is equal to 0. So you can take that minus I omega p outside. Take minus I omega p outside. Then you end up getting an AP with a minus sign, because I took minus I omega p outside. But this is exactly the same as the gradient term, except for a minus sign in between. And instead of k here, I will pick up an omega p. Minus I will take care of itself because I am going to take its complex conjugate and multiply. Okay? So the next term which I will have will be half integral d omega p. I will have 1 over 2 omega p and an omega p square, which is fine because that is just omega p by 2. Then I will have AP minus A minus P dagger, AP dagger plus A minus P. minus. Okay, this is what we have. We don't need this anymore. Okay, so what is this? Okay, so everything up to this point goes for a ride, and I only have to work with this. Now you find that there is an AP and an AP dagger, and there is an AP and an AP dagger. They are going to come with the same sign. So let us start with that. So integral d omega p by 2 there is an AP dagger. There are two of them, one from this and one from this. Similarly, there is a minus P dagger and an AP, and an A minus P dagger and an AP. This has minus sign, so they come with the same sign. So plus 2 times A minus P dagger, A minus P. The claim is, if you have done everything correctly, the remaining 10 should go away. If they don't, I will just say they go away and you sort it out. So let us see. So there is a AP and an A minus P here, and there is an AP and an A minus P here with a minus sign. Once that goes away, the other will go away because it is only a Hermitian conjugate. So this is what we have. It's actually slightly non-trivial. That is why I am going through the whole work. I mean, because it is not discrete system but continuous system, you have to be always careful about what you are integrating over. There are infinities coming because of infinite space, and there are infinities coming because there are infinite number of modes, and you have to disentangle these two. So you have got up to this. So now I can take away this 2, and this 2. Okay? And I can also notice that the P can be replaced by minus P because the omega P and this integrations are the same. So this is just this minus sign and this P will go. So the only difference is the A and A dagger don't commute. So one term comes with A dagger and the other term comes with A dagger A. This is exactly what happens in harmonic oscillator as well. There will be only one mode, that is all. What will happen at this stage in harmonic oscillator is that you will have a dagger here, and there will be an A dagger A here. We only want to have A dagger A, which is the number operator. So A dagger you write as 1 plus A dagger A. So your 1 will come, and this will become 2 A dagger A. You divide by 2, 1 will become half, and this will become A dagger A. So A dagger A is the number operator, n plus half times this. Now we want to see what it gives here. So here it is, as I said, slightly tricky, but not too much. So you want to rewrite this in terms of this quantity. Okay. First, let us expand these things out so that those problems are taken care of. So this is d3p upon 2 pi the whole cube. Then there is an 1 over 2 omega p that gives me half, yet another half. Okay. Then I want to write these A's in terms of our original A daggers. That is going to give me a 2 omega p. Because this I am going to write as square root of 2 omega p AP. It's convenient to work in terms of those AP coordinates because the normalization we want it to be just Kronecker delta replaced by a Dirac delta. We don't want a 2 omega p there. That was thrown in order to show manifest Lorentz sequence. So once I do that, I will have 2 omega p's coming out of that in all the terms. So that takes away the 2 and gives me an omega p, and this capital A is become small a. These are just like harmonic oscillator objects because they have on the right hand side 2 pi the whole cube Dirac delta function of p minus q, which is a continuous version of the discrete delta p cube for a discrete number of harmonic oscillators. So you go to this and you want to write this in terms of this quantity. So you write this quantity as the commutator, which is 2 pi the whole cube, Dirac delta function of P minus P, which is 0. So you put as 0 plus A dagger of P AFP. Okay, this is Dirac delta function of P minus Q with a Q going to P. I mean, it will be interpreted as a volume, so that is not an issue. So this is what you have. This replaces this term. So your entire Hamiltonian turns out to be integral over d3p upon 2 pi the whole cube. There is a half, and this A dagger p added to that will give me a 2 A dagger p. So that term is fine. You get omega p A dagger p AP. Then you have the second term, which is plus integral over d3p upon 2 pi the whole cube half omega p, and this quantity you interpret as the volume of the space. I mean, let me just explain to you where that comes from. It's something which you have done in Fermi's golden rule in quantum mechanics, but it might not have been introduced in this form. What we are doing is fairly elementary. We have the relation integral over d3x of the pure space e to the I x dot p minus q. Normally we would have written p minus q dot x, is the same thing. X dot p minus q equal to 2 pi d whole cube in our convention. Dirac delta function of p minus q. Okay. What we have got there is a Dirac delta function in the momentum space with zero separation. So you take the limit of p going to q on both sides. Then you end up, when p goes to 0, you end up getting integral d3x is equal to 2 pi the whole cube, purely formally, Dirac delta function of zero. But this is just the volume of the whole space. Okay? And now you can do the whole thing much more rigorously by discretizing, putting a box and then taking discrete indices and taking the limit and all that, and you will get the correct result. So if you do that, this can be written as essentially the phase volume integral v d3p upon 2 pi the whole cube half omega. So this is the final answer. So the basic point is that the final answer blows up in your space. If you consider the expectation value of this in any state, in particular the ground state, this will give you 0 because the number operator on that state is 0 and the ground state is normalized. So the expectation, this is a C number, so it will give you 1 and this will survive. So the vacuum expectation value of the Hamiltonian is given by this expression. Now this has two infinities. One infinity comes from this v, which is an integral over d3x. I could actually written it as a phase space integral, d3x, d3p upon this quantity. Okay? That we don't care, because we know that we are integrating all over the space, and if there is some finite energy density and if you sit through all space, because the vacuum is translationally infinite. Suppose the vacuum has some energy, whatever it is going to be same here as well as there. So when you integrate over all space, unless that energy is 0, you are certainly going to get a infinity due to volume. That is not scary at all. You can work in terms of energy densities. So you compute the h divided by the volume of the space, volume of the real space, and ask how much it is. So this we don't care. The problem child is the second term, because this omega p at large P goes as P, and there is a d3p integration which is p square dp integration, and that diverges. Okay. So why did we, this is very important, so let me spend some time about it. The reason it came about is because you said that your relativistic particle has to be interpreted in terms of a whole bunch of harmonic oscillators. We saw no logical flaw in it. But harmonic oscillators come with 0 point energy half h cross omega. There is no way you can get out of it. And if there are infinite number of oscillators, you have to integrate it and you get an infinite value. So in conventional high energy physics, and depending on whom you talk to, most people will say this is not a problem. Okay, they will say you just subtract it out. Now I think it is completely wrong. I think this is a problem. We don't understand the answer to that. But we live with it, because most of the time you can do something to get out of that. But I don't agree with the point of view that this can be taken away. The way it is taken away formally is to introduce a concept called normal ordering. And that I want to introduce, because you will go and read some other textbook and you need to know what it is. Suppose you have any expression, like this expression for the Hamiltonian density. Okay? The expression for the Hamiltonian density is given in terms of A's and A daggers. Then you say that if an operator is given, you denote by usually normal ordering is denoted by an expression like this with 2 columns on both sides. Okay? This stands for, you take your original expression and quietly flip all the A daggers and A, so that all the A daggers are on to the left of the A's. And don't add or subtract anything, you just take the normal ordered expression. So if you do that, then obviously you won't have a problem. If all the A daggers are to the left of A, then vacuum expectation value of that expression will vanish. And when we come to complex scalar field, we again will have to resort to this in order to make the charge of the vacuum state to be 0. Otherwise it will not be 0. So whenever you take ground state expectation value, there is a contribution which comes from this extra term. So I went through this elaborate detail to show that there is no trickery involved. I mean, you do a honest straightforward computation and you will get this result. And the moment you assume that there are infinite number of degrees of freedom in this D3P, you will end up get a divergence from the second term. Okay. So if the expression is normal ordered, then this will go. Another way of doing this would be to go and subtract from every harmonic oscillator Hamiltonian half h cross omega. So you argue that, well, you know, I don't know what the Hamiltonian for the system is. It could have been h or it could have been h minus half h cross omega. Then you go and say that, okay, if the h has to be subtracted, then the Lagrangian should have a plus half h cross omega, right? So you are, but then the Lagrangian for this system has to be with this for every degree of freedom added up. So your formal Lagrangian is infinite, because you have to integrate over infinite number of degrees of freedom. You are adding an infinite constant. So somewhere along the line you have to add or subtract an infinite constant, and how you do this is your business. Without that you cannot get out of this. What happens if you go and compute the momentum of the ground state? Okay, so we did the whole thing for the Hamiltonian, but I can also write down an operator for the total momentum. How do I do that? We had done this before, because we had obtained an expression for T0 alpha. So if you look at T alpha 0, we had a term which went as, let us say, pi d alpha of phi, or I should probably put up there alpha again, doesn't matter. Okay, so these are the special components of the momentum density, and you can integrate this over d3x to compute the total momentum. I mean, the Dij will have another term which is a Kronecker delta Ij times Lagrangian, that goes away when you are taking 0 and alpha. So this is the only term which will survive. So if you compute that, I am not going to do that. If you compute it as identical computation, and you see, instead of having a same kind of object, this is phi dot and d alpha of phi. So you can go through the computation and you will find that you are essentially going to end up getting exactly the same kind of an expression. and instead of omega p, which is the energy, you will get the momentum vector p. Okay. So here you can't do anything. There is a momentum vector p times the number operator p in that, and number operator p can have any kind of dependence on p. However, here instead of this thing, you will have a p. So you have an integral degree p of p. Now, depending on your point of view, you can set it to 0 or infinite, and most people will set it to 0, and it is very good reason, because it is an odd and even function. So for every p, there is a minus p, and when you are adding all of them up, the vacuum state does have 0 momentum, but it has infinite energy. Now the question is, does it violate Lorentz invariance? I mean, can you have a system which has some amount of energy, non-zero energy and 0 momentum in all frame? Yes, you can, provided one of them is infinite and the other is 0. So when you make the Lorentz transformation, again you will find something is infinite and something is 0. But in no other case you can do that. But as far as the momentum is concerned, you don't run into this trouble. But as far as energy is concerned, you do run into this trouble. Okay, fine. Okay, maybe that is a good place to start. Next, I wanted to talk a little bit about charges associated with charges and the associated symmetries, and I want to prove that Goldstone theorem in generality, and then we will take up electromagnetic field. Complex scalar field I will probably briefly mention, and then we will take up electromagnetic field. Okay, let's start. Yeah.
So when you do this thing called the complex scalar field, will you say that you will have non-zero charge for the?
Yeah, I'll do that. At least I'll indicate how the steps go. That is actually slightly more serious, and you have to do a normalization for it. Yeah.
So then there should be a corresponding problem with fermions or something else, right? And there should be some
No,
charge.
it is not. You can, once your normal order vacuum will have 0 charge. That's what you do. Just as vacuum has 0 energy. Yeah, you put up the hand and he asked the question.
It is not that way. So, did you mention anything about how this can affect gravity?
No, I did not, because nobody really knows. Since you asked the question, let me mention the following. This by itself, if you subtract it away and ask whether it affects gravity, the answer is it doesn't seem to. Okay? With any reasonable cutoff, you can ask what kind of curvature will be produced, and you find that such curvatures are not seen. So somehow nature is able to get around that. Whether that is because we have misunderstood gravity and its relation with matter, etc., we don't know, but it doesn't seem to practically affect it. But the reason I mentioned all this is that I am going to have a detailed discussion of something called Casimir effect. Okay? The whole philosophy in this course is to concentrate on things which you may not find adequately discussed in other textbooks. So that is why things like perturbation theory, etc., I am going to do only very little, which you will find in so many books, and there are excellent discussions. So I will spend time on Casimir effect, and Casimir effect tells you that at some level this is real. One interpretation of Casimir effect, not the only interpretation, but one interpretation of Casimir effect is in terms of the modification of the 0-point energy due to boundary condition. Another example which I will discuss is something called Unruh effect, which is that the vacuum state which we have defined here, which we thought was 0 temperature and whatnot, will appear to be a finite temperature state to accelerated observers. And that again comes because the vacuum fluctuation has a different pattern as seen by an accelerated detector. It is not generally covariant, it is Lorentz invariant, but it is not invariant under general coordinate transformation. So we have enough machinery already built up, so it would be a pity not to discuss that, so I will do that. So in both the cases this will come up. So the moment you have Casimir energy being real, you can go back to your question and ask, does Casimir energy gravitate? That is a more operationally well-defined question. Suppose I haven't discussed Casimir effect, but I am assuming some of you will know this. It essentially tells you that if you have two parallel plates, like in capacitor plates in electrostatic, except that you don't put any charge on it. Okay, these are 0 charge metal plates, formally infinite, or their sizes are much bigger than the separation. You keep it in the vacuum, then they will attract each other for no good reason. Okay, and this is called the Casimir effect. It has been observationally detected. This Casimir energy has to gravitate. If it doesn't gravitate, I can make nature do bad things. That is very simple. I mean, one way of doing this is you put it over a pulley and you put a mass here. Then you tie this over another pulley and you put a mass here. Okay? So you adjust the masses so that this is some earth or something. So the weight of the masses is just holding it apart or whatever. Or you arrange masses in such, at a given instant you put some extra masses and take away some masses. I mean, you do some experiment like this. What you want to do is you go to a faraway place and measure the gravitational field due to this entire system. And you can also take Earth's gravitational field. That doesn't affect anything. Once you take out some of the masses from here, these two are going to attract, so these two things are going to go up. Now you are interested in measuring the gravitational field produced by these masses. We know from standard general relativity that if these two things are moving and you measure the gravitational field, it will get contribution from its kinetic energy. Okay? Now, if the source which is producing the gravitational field does not satisfy a particular identity, the covariant conservation of that energy momentum tensor, then Einstein's equation will go bonkers. You cannot satisfy the Einstein's equation and find a consistent solution. Therefore, if these two things are going up, that energy has to be compensated by the, see, if there is some energy has been given to this, that much energy has to come from this attraction, which is what it does, because there is a force of attraction between these two. There is a total amount of energy which is stored here, and that has to go down, and that is what is making the work. If this does not gravitate, but these two masses gravitate, then you run into a contradiction. So by this elementary thought experiment, and you don't want a contradiction with the gravity at far distance, you can come to some rather profound conclusion that the Casimir energy between two capacitor plates where the Casimir effect has been observed in the lab must have a gravitational effect. But then by observation we know that Casimir energy is finite. So it is only the finite residue which seems to gravitate. I mean, at least this thought experiment only tells you that that finite residue has to gravitate. But if that finite residue gravitates, and if that finite residue is interpreted as due to half h cross omega and a boundary condition, then it looks very, very surprising that the half h cross omega does not gravitate. But it doesn't, because you can compute this with a cutoff and ask, given the curvature on Earth or whatever, what should be that cutoff, and it's some ridiculous number. So with any decent energy scale cutoff, there is so much of energy that the curvature should be so strong, which we don't see. Okay. So there is a open, unsolved problem here, waiting for somebody to get a Nobel Prize, as to why this contradiction arises between these two. By and large, in high energy physics, this will be ignored. People know this problem, people know that it requires solution, but since we don't know the solution, people don't want to talk about it.
So,
Yeah.
so what I mean when I ask the question is, when we define compression relation between phi and phi operators,
Yes.
and we say derived data function is not our type, only spatial.
Yes.
And then we when write Hamiltonian, Hamiltonian contains m square phi square term.
Yes.
And this term is due to relativity.
What is due to relativity?
Energy due to mass.
No. Okay, let us go back. How do you quantize the system in Heisenberg picture? In order to quantize the system in Heisenberg picture, you start with a classical system. You identify the dynamical degrees of freedom and the canonical momenta from the classical system. You identify the Hamiltonian from the classical system, and then you say that we upgrade the C numbers to operators and impose the commutation.
Yes.
Now, what is our classical system? Our classical system is a fully relativistically invariant scalar field.
Yes.
It has a Hamiltonian. The form of the Hamiltonian is pi square plus del phi the whole square plus m square phi square.
Yes.
So that is what we take.
Yes, exactly. And,
Huh.
and that's why we cannot have four-dimensional.
No. That is not the reason.
No, then we built in contradiction.
Why?
If we solve this way with that Hamiltonian
Right.
and using Heisenberg equation,
Yes.
then we are not having the same result if we take four-dimensional data function.
No, we will not have that result with four-dimensional delta function is true, but it has absolutely nothing to do with Lorentz invariance. You see, what if you compute that 5 pi expectation value,
Yes.
you get an expression on the right hand side. It's complicated to write down because it's a Hankel function, but you get an expression. You write it down. The right hand side is fully Lorentz invariant, correct? Now you take the limit of t naught x naught going to y naught. Then you get a 3-dimensional Dirac-Delta function. So there is absolutely no contradiction with Lorentz invariance anywhere. Okay? And the other point which you have to remember is that the Heisenberg picture inherently works in a 3+1 approach. Because the Hamiltonian is just one component of the momentum. In fact, next day when I am going to discuss these charges, I will write down another equation which is essentially that minus I dl of any operator is actually PL that operator. Okay. So from this point of view, you see that everything is fine in some relativistically invariant way, and that is why I use that partial symbol.
Yes.
Because I can use the same relation with instead of t, I can use with x, and right hand side will be just the momentum generator. So this is true for any symmetry, and PL and this thing generate translational symmetries in space and time. So none of this has any problem with Lorentz invariance. I mean that is one thing which can be proved. It is not manifestly Lorentz invariance, but the theory is Lorentz invariance. That is why you have Amsler. And also 5 pi has a dimension.
Yes.
You see, 5 times pi's dimension cannot change, and that dimension has to be 1 upon L cube. So it can never have a 4-dimensional Dirac-Delta function, right? Because phi has dimensions 1 by L, pi is phi dot, which has dimensions 1 by L square. So the dimension on the left hand side is 1 over L cube. So you cannot have a 4-dimensional Dirac-Delta function coming there. Yeah.
When you were doing the last thing over there, you put integral d to p equal to 0, right? Because it's odd.
Yes.
And you said some people can take it to be infinite.
No, I was joking halfway through in the sense that you can, it requires a subtraction of 2 infinities. See, somebody might insist that I am first going to integrate over all positive p, and then I am going to integrate over all negative p. So one term will be plus infinity and the other term will be minus infinity. But a sensible answer for that, I agree, is always 0. That is because you can put a cutoff in that. There are very formal regularization procedures which we will discuss later on. When you do that, this term will go to 0.
Then when you substitute for the delta function as Boolean, right? Over there.
Yes. Yeah.
So if you have to actually put it as delta function,
Yes.
then we take a limit of Boolean going to infinity, and
Yes.
then it becomes a delta function.
That's correct.
And we have used that everywhere because we have substituted for p by q and w. So in the end, the expression that we get formally in the
You can write this formally as d3x d3p upon 2 pi the whole cube half h cross omega.
Yeah, so I'm asking, like, for a finite volume, will the expression make sense? Because we have used the delta p minus q is.
Yeah, actually in a finite volume the expression will make sense if you use what is known as a box normalization. So what you do is you repeat the entire calculation, but you don't take e to the minus I p dot x as the waves, but you take it with the p discretized. So you take a large cubical box and you say that the only modes which you are calculating are the p, which is, let's say, px is equal to some n pi upon lx kind of a thing. Then you can repeat this whole procedure, and the integrations now over space will be confined to a finite region, and your integrations over p will actually be summation over the discrete indices. As a result of which, that d3x integration will not give you any terror, and that will actually give you volume, the normalization volume. But d3p integration is a different kettle of fish, because the second the divergence which comes from here is an ultraviolet divergence. It comes because there are infinite number of modes with frequencies above any frequency, or infinite number of modes with wavelengths below any wavelength. So you take any given wavelength and there are infinite number of modes below that wavelength. So even if I put a large box which regularizes things at large spatial scale, it will not regularize things at small spatial scale. So even within a box, there are infinite number of modes because it can wiggle infinitely at infinitely small scales. So that is why the divergence from V is trivial and it is completely understandable. But the divergence from D3P is in some sense more profound.
And we calculated the H and we had put omega p here, and to calculate the P, you just had to replace omega p by
Okay.
the same expression.
No, you should try it out. I mean,
Yes.
don't take my word for it. Yeah, that is what will happen. Yeah.
No, I was just wondering because the general charge, if there is some property, because there is a number operator and there is a half sitting there.
Yeah, that is true. I mean, for example, any extensive object, so to speak, like momentum for each particle, you are adding them up, that will give you the total momentum. Energy for each particle, you are adding them up, it will give you the total energy in non-interacting theory. And when we do complex scalar field, we will find that the same thing happens for charge. And that is why you need to do the same trick for charge as well, because if you take the charge of each particle, in the complex scalar field, you will have A's and B's, A dagger and B dagger, and they will have opposite charges. And that will also add up like this. So in that sense, it is a general feature. Any property of a single particle, if there are each excitation is thought of as a particle, then they will just add.
But then will there be half factor for the charge, like the extra half factor?
We will do that. So that depends on how you define your charge, and you can always define your charge that it carries a charge Q. I mean, Q is, we know that charge, unlike everything else, like energy or mass, is quantized. So it comes in some fundamental unit. So there is a very natural Q which you can use. The current which you write down is, if a current J mu is conserved, alpha times J mu is also conserved. So it doesn't fix your normalization. So the normalization has to be fixed by some convention, but you choose it in terms of electronic charge. Yeah.
One more thing, like when you were doing that, first you took a phi square and then you put it as phi dagger, right?
Yes, that was just a trick. You could have worked with phi square, you would have got the correct result.
Yes.
What you would have got is
Delta function will be P plus
exactly. You will have to deal with the Dirac delta function of P plus Q, and you have to, anyway I miss minus signs. So if I have a P plus Q, there will be more minus sign to worry about. So that is purely a trick.
No, it doesn't have like you put t equal to 0 and suddenly you have this field that is phi. Then you have phi equal to phi dagger at t equal to 0, right?
Yeah, but phi is equal to phi dagger at all times. It's a Hermitian scalar field.
But you don't need to use that. I mean,
I don't need to use that. That is just a
Fine,
cute
yeah,
trick
yeah.
to take care of it. And that's all. Yeah. Any other? Yeah, okay. Next week, I think there is one day when we can't have class. Let me just check this out. We have 28th the science day going on, right?
Yeah.
And 28th is a Tuesday. Okay, so this room will all go, right? Various things will be happening. So 28th there is no class. So Tuesday there is no class. We will start on Wednesday.